Hi, I'm Rachel from ARM. My topic is embracing high performance storage with OpenARM. It's about our practice of SPDK on ARM64. SPDK is the storage performance development kit. It provides a set of tools and libraries to create high-performance, scalable user mode storage applications. This picture shows the SPDK's architecture. It mainly includes 4 layers. From the bottom up, it's the driver layer, including NVMe driver and so on. And then the block storage layer. It includes the NVMe block device and the Linux AIO block device, IO Urim block device, and many others. And this layer is the block storage service layer. It provides several services for different purposes, like logical volume, RAID, open channel, and so on. And the top layer is the storage protocol layer, including the MemFabrics, the Vhost targets, the SPDK targets, that are capable of serving disks over the network or to other processes. Besides, it implements BropFS as a file storage service. We know that traditional kernel I/O stacks bring obvious overhead due to context switch, data copy, interrupt, resource, synchronization, and so on. SPDK can minimize the impact on CPU and memory bus cycles during I/O processing, mainly by 3 ways. One is it uses the user mode for storage applications rather than the kernel mode. The devices that SPDK test control are unbound from the kernel space driver, and instead UIO or VFIO driver is used for SPDK to operate devices directly from user space, which thereby eliminates costly kernel context switch. The second is that SPDK runs in a pod mode instead of interrupt mode. When SPDK initializes, on each core runs a thread. It's called a reactor, and users can register different pollers on this reactor. Some of these pollers then poll the devices for completions instead of waiting for interrupts. And this reduces the related interrupt handling overhead. And the third one, the shared nothing thread model. Each thread operates on its own resources for threads communication. SPDK doesn't use a traditional lock mechanism, but using event ring mechanism. For a NVMe device, a hardware queue is only ever accessed from one thread at a time. SPDK can send a request to the device from multiple threads in parallel without locks. It's these 3 key techniques that bring SPDK's high performance. And about SPDK, we have contributed more than 50 pages to enable and optimize SPDK on ARM64, including the optimization is about memory barrier and base64 and CRC32 and the ISAL library. And in the following slides, we will walk through our practice about running SPDK NVMe-over-RDMA and SPDK Vhost target on ARM servers, and our implementation of SPDKcsi to bring SPDK to container storage. At first, I will introduce the MemFabrics. NVMe is an interface specification optimized for solid-state storage for both client and enterprise storage systems utilizing the PCIe interface. One of the main distinctions between the NVMe and MemFabrics is the transport mapping mechanism for sending and receiving commands or responses. For local PCIe, for local access, NVMe maps the commands and responses to the shared memory in the host over the PCIe interface protocol, while MemFabrics uses a message-based model for communication between a host and a target storage device. And currently, we have NVMe-over-RDMA, over TCP, and over fiber channel. For RDMA transport, RDMA is a host offload host bypass technology that allows an application, including the storage application, to make data transfer directly to or from another application's memory space. And it requires the spatial NICs, the RDMA-capable NICs, to manage reliable connections between the source and the destination. And similar to the NVMe QPS, applications communicate with the RDMA NIC using the dedicated QPS, including its QPS include the send queue and the receive queue, and also it requires the completion queues. And for NVMe over RDMA, each NVMe queue pair, this is NVMe queue pair, each NVMe queue pair is mapped to a RDMA queue pair, and each set of the queue pairs is aligned to a CPU core. Then NVMe commands are put into the RDMA QPS and sent over the NIC. This chart is the comparison of the NVMe over RDMA and local PCIe on ARM server. We use NVMe 750 in target and uses the Mellanox NIC. The data is tested with the 4 kilobyte payload size at 128 Q depth. We can see there from this picture, there is little change with the number of CPU core. For in this platform, one core can almost saturate this full NVMe SSD, and except for the one core rent rate case, in most cases, the performance of NVMe over RDMA is close to the local PCIe's performance. To use NVMe over RDMA, we said before, spatial NICs are required. However, NVMe over TCP makes it possible to use NVMe over Fabrics across a standard Ethernet network. There is no need to make configuration changes or implement any spatial equipment. When using a TCP transport, each NVMe queue pair is mapped to a TCP connection, and NVMe commands are encapsulated and then sent over the standard TCP IP sockets. Currently in SPDK, NVMe over TCP, there are 4 types of socket implementation. The POSIX socket, URIN socket, and VPP and C* sockets. The POSIX socket is the most stable one, and it has no dependency on the kernel. URIN sockets, leverages the new Linux asynchronous I/O interface called IOU ring. It's built around a ring buffer in memory shared between user space and the kernel. And it allows the submission of operations and collecting the results without the need to call into the kernel space in many cases. But it requires the kernel version newer than 5.4 and 0.3. VPP socket. VPP is the vector packet processing. It's a fast network data plane designed on top of DPDK to run the network workloads using vector packet processing technology. But the integration test with VPP will be stopped in SPDK 20.111 due to the performance limitation. And C star is an event-driven framework allowing you to write non-blocking asynchronous code in a relatively straightforward manner. Some of the work of C star sockets has been done, but still needs further investigation. Currently, we have tested the U-ring sockets and the POSIX sockets. This data is tested from another type of NVMe SSD, P4600 in the target. It's also tested with the 4 kilobyte payload size and 128 Q depth. This is the comparison of the POSIX sockets and the U-ring sockets. Generally, with the number of CPU cores, the bandwidth is getting better, and at about 8 cores, it can reach the NVMe's full performance. From comparison, we can see that the performance of U-ring sockets is not obviously better than POSIX sockets. For kernel IO U-ring has 3 main modes. One is the interrupt mode, and the other 2 is a pull mode. From my view, it's the pull mode that should have better performance. But now SPDK only supports U-ring's interrupt mode due to some limitation, and the community is still doing optimization on this. The above introduced is all about the SPDK's NVMe-over-Fabrics. It's used to provide storage for remote clients. SPDK also can be used to provide backend storage for virtual machines. SPDK Vhost target is designed for this purpose. Before I introduce the Vhost target, I will explain some related concepts. One is VirtIO. As I write here, VirtIO is the I/O virtualization specification. It's an abstraction layer above a set of common emulated devices in a virtualized hypervisor like QEMU. And it provides a common mechanism and layouts for device discovery and configuration. Also provides common mechanism for front-end driver and back-end driver to communicate. And VirtIO offloads parts of operations to host is called Vhost. It includes the Vhost kernel and Vhost user. For the difference is for QEMU VirtIO is QEMU that deals with state with guest. But for Vhost kernel, it's the Vhost module in the kernel space transfer date with the guest. And for Vhost user, it's the Vhost backend in the user space that transfer date with the guest. So Vhost user protocol makes it possible for guests to transfer I/O dates with a user space process like SPDK. And Vhost user protocol defines two sides of the communication. One side is master and the other is slave. Master is the application that shares its vote queue. In our case, it's QMU. And slave is the consumer of the vote queue. In our case, it's the SPDK Vhost target. In this picture, we can see that the virtual machines shares its huge page memory with SPDK Vhost, and SPDK Vhost transfer data with the virtual machine through the vote queues in the shared memory. And for control path, Unix domain socket is used to transfer control message between these two processes. Now, SPDK Vhost supports Vhost-scsi, Vhost block, and Vhost NVMe. And the Vhost NVMe is still experimental. You can refer to SPDK documents or the source code for details. And this is the general introduction of how SPDK provides storage for virtual machines. And to bring SPDK to container storage, we designed SPDKcsi plugin. CSI, the container storage interface, it's a standard for exposing arbitrary block and file storage systems to containerized workloads on the container orchestration systems like Kubernetes. And it's a general protocol, not for Kubernetes only. CSI consists of the controller driver and the node drivers. The controller driver is responsible talking to the service provider to create or delete the volumes, and the node driver is responsible for mounting or unmounting the remote volumes to the host, to the local host. For example, we can deploy a controller driver on a container's master node, container orchestration's master node here, and a node driver on each of the worker nodes. For the communication between the container orchestration and the CSI drivers, we use the RPC messages for this communication. And for Kubernetes, Kubernetes has supported the CSI spec 1.0 from release 1.13. In this link, there are a set of CSI driver which can be used with Kubernetes. Our new CSI driver, SPDKcsi, aims to bring SPDK to Kubernetes storage through the MemFabrics or the SPDK protocol. And it should support dynamic volume provisioning and enables pods to use SPDK storage transparently. The CSI driver will be an executable wrapped inside a container to be deployed in Kubernetes cluster and implements SPDK storage class. And this project is initiated by ARM. It has been released in SPDK 20.111. This picture is the SPDK CSI's overview. It mainly contains 3 parts. This part is Kubernetes is a Kubernetes cluster with one master. It's here, one master and 2 workloads. This workload and this workload. This workload runs a CSI node driver and a work pod running the engines. And this workload runs a CSI controller driver. And the CSI RPC is sent from this master to these 2 driver CSI driver. And this part is a Kubernetes cluster running some SPDK nodes with NVMe devices and SPDK software stack. And this part is the networking between the Kubernetes cluster and the SPDK storage cluster. The CSI controller driver, this driver talks to the SPDK's JSON RPC service through the controller network, and the CSI node driver here. The node driver connects to the SPDK NVMe-over-target, NVMe-over-fabric target through the high-speed data network like RDMA or TCP. And the status of our SPDKcsi project is that mandatory CSI functionalities are ready now, and there are still lots of work to do. So what's next? Sorry. During the following times, we will for NVMe-over-fabrics, we will continue to integrate and optimize SPDK NVMe-over-TCP with MTCP as the user space TCP stack. And we will try to optimize SPDK NVMe-over-TCP with the urine socket. For SPDKcsi plugin, we'll continue the tests and improvements for production level quality. And also we will introduce some new features like the topology, volume expansion, snapshot, and so on. You can refer to this Trello board for the details. And we will also integrate it with Look to build a total solution of leveraging SPDK in Kubernetes. And we welcome your contribution to SPDKcsi project. You can refer to the following links to get more information and guidance. That's all that I share with you. If you have any questions, please send me an email and I will respond as soon as possible. Thank you.